I thought today I will discuss mainly how to homogenize fully nonlinear equations, give at the beginning an idea of how you do it in the periodic case, and then when you do it in the ergodic case. So let me start by giving you the basics of the basic tools I'm going to use. One of the fundamental tools of all the theory of fully nonlinear equations is the Harnack inequality, Krylov-Safanov-Harnack inequality. Krylov-Safanov-Harnack inequality says the same as the Harnack inequality for non-divergence equations. So if you have a solution of an elliptic equation in non-divergence form, the aij's, you can assume them as smooth as you want, but the problem is that you are not asking for any a priori modulus of continuity. So they can become, as it will happen in homogenization, highly oscillatory, right? Nevertheless, the Krylov-Safanov-Harnack inequality says that if you have a non-negative solution, if it's a solution in, let's say, a unit cube of Rn, in Q1 of Rn, U is bigger or equal than 0, and let's say you normalize it at one point, then the sup of U in the half of a cube is bounded. It's a constant that depends only on the oscillation of the coefficients. That is on lambda and lambda. So basically, the picture is the following. You have the cube, you have a solution, and you have control at one point. Then, in the cube of size 1/2, you have control. Well, here it should be very high, but some constant, depending only on the modulus of continuity, on the oscillation of the coefficients. What makes this Harnack inequality so valuable and so powerful is the fact that it lives in a different scale invariant. In other words, you look at the divergence or non-divergence case, both the DiGiorgi-Nash-Mosher Harnack inequality and this Harnack inequality had the strength that if you rescale the function, you do U of lambda x, it satisfies another equation where you are evaluating the aij's at a different point. Okay, and so the natural scaling invariance for this. So what you can ask, what are the families of equations which are scaling invariant? And then the first family is constant coefficient. And any continuity you put in the coefficients, if you make a blow up a sequence of dilations, the coefficients become constant. Okay? And so that's why all of the theories, Schauder theory, Calderon-Zygmunt theory, and so on, should be thought as small perturbation theories. Basically, if you look at the proofs, they say, okay, I know the theorem for the Laplacian, and if the coefficients are Helder continuous or the coefficients are of a small oscillation, I know by a bootstrapping argument the theorem for these coefficients. Okay? What is powerful about this inequality is that it goes to another family of invariants, which is just equations, bounded measurable coefficients. That is, we are in the family of equations such that aij is between lambda the identity and lambda the identity. So you can rescale in this family and fall against in this family. So and that's what makes the Georgis and Krylov-Safanov-Harnack inequality so powerful, because it's a different scaling invariant. This is there is this famous sentence of Peter Lux that linearity breeds contempt. one way to say continuity breeds content, because you do linearity with discontinuity, you are in trouble. Okay, this Harnack inequality, you can make it more or less flexible, you can modify it. For instance, if you put a bounded right-hand side here, then you have to correct for the right-hand side according to your scaling. So in the ball of radius 1, if you put the bounded right-hand side, the theorem still will be true, because you can correct by adding minus x squared and making out of the function a super solution, or adding plus x squared and make out of the function a sub-solution. Okay? In other words, if I do aij of x, dij of u plus x squared, then this is f plus sum of aii. And so from, let me put here a constant, right? So here I have a constant. And therefore, since A is uniformly elliptic, the trace is strictly positive, is bigger than n times little lambda. And so no matter the sign of f, this will become positive. Or if you add, since we are in the cube of size 1, or in the ball of size 1, instead of adding this, you add 2 minus x squared to keep the positivity of the sum, right? Then you get f constant 2 minus x squared. You get f minus 2 constant sum of aii, and this is negative. And so you can use the fact that the function is not exactly a solution, but is near super and sub solutions to obtain the same result. Okay, so the Harnack inequality has this flexibility, which I'm going to use later, that if you add something bounded, then it's more or less still valid. Okay, I mean, doesn't have, it's valid in this form, right? Usually you can also write the Harnack inequality as the sup is controlled by the infimum, and this is not true, because you take x squared, right? It has a right-hand side, and the sup is not controlled by the infimum. But up to a constant error, the Harnack inequality is true if you put a bounded right-hand side. Okay, why is it so important? Why is the Harnack inequality so important in the theory of fully nonlinear equations? It's the same as when you do divergence equations. When you do divergence equations, right, you have an equation dj fj of gradient u equal to 0, right? And then there is a triviality, but it has been very helpful. Serrin told me once, and I have been very helpful, so let me give it to you. This is following. Whenever you have an equation that has a comparison principle and is invariant under translations, then the first derivative always satisfies something. Okay? And the reason is the following. So suppose I have an equation like this one, right, which is invariant under translations, and is invariant under translations, and has a comparison principle. If you have two solutions, u1 bigger or equal than u2, then u1 cannot touch u2 unless they are identical, right? For instance, take the minimal surface equation as an example. So the minimal surface equation, right, is divergence of gradient u over the square root 1 plus gradient u squared. It's an equation of this, is invariant under translations in Rn plus 1, right, because it doesn't see constant. Okay, and then I say a consequence of this is that if you have a minimal surface with nice data in a nice convex domain, then it's Lipschitz inside. Okay, and the reason is the following. You take the minimal surface, right, and you make it, and you control it on the boundary with barriers, with planes, right? So the first thing you say is, okay, I can take planes, and so I can show that along the boundary, the minimal surface is Lipschitz. Okay, because you can, if the domain is strictly convex, you can always put a plane by above and a plane by below. Okay, and once you know Lipschitz on the boundary, what you do is you make an infinitesimal translation. Now we look from above, right? And I translate the configuration a little bit to the right. Okay, so I translate this a little bit to the right, and I lift it a little bit. Okay, and since I know that near the boundary is Lipschitz, when I lift it, I know that over here the translation is epsilon above, just by lifting it a linear factor, the translation is above the solution. So if this is u and this is the translation to the right and a little bit up, right? So I have this, I translate to the right and a little bit up. Okay, and since I know Lipschitz at the boundary by using the planes, then I know that along here u translated is bigger or equal than u. That is u of x plus f minus epsilon h minus plus constant times h is bigger or equal than u of x along the boundary. Okay. So you divide by h, and you have, but if it is bigger along the boundary, since we have a comparison principle, it's bigger everywhere. And then you subtract and divide by the constant, and you get that u of x plus epsilon h minus u of x over h is bigger or equal than minus a constant. Okay. So this is a very good principle. It's a very important principle. I mean, it's very simple, but it's a very important principle. And all you use is that you have an equation invariant under translations with a comparison principle. Okay. And that's why it's not unreasonable. Yeah, you can see directly a posteriori just by taking a derivative of the equation. Okay. So the same happens with fully nonlinear equations. So let me go through fully nonlinear equations a little bit and deduce estimates for a fully nonlinear equation. So as I mentioned last time, a typical fully nonlinear equation is an extremal equation. So a typical f of d squared of u equal to 0 is to take you have a soup of a family of linear operators. So you have a family lambda alpha of u. Let's say sum of aij sub alpha of x dij of u, okay? And you want to find the extremal function, a function u0, for which the soup of L alpha of u over alpha is equal to 0. Last time I gave you the example of the Pucci extremal operators. You take the identity and a multiple of the identity, and you look at all the operators aij that have ellipticity fluctuating between these two numbers, and you want the supremum of that equal to 0. And I say that for that, you have to find a function u0 for me such that, so find u0 that satisfies the following nonlinear equation. Take the square of u, which is a matrix at any given point, take the positive eigenvalues, separate the positive eigenvalues and the negative eigenvalues. And basically what we are trying to do is we are trying to construct the most concave possible function among all of those solutions. And the most concave possible function is the one that has the smallest possible positive eigenvalues, eigenvectors, eigenvalues. Okay? So the operator is that this has to be as small as possible. That means that they have to balance this one with the largest possible constant. So capital lambda, well, too many lambdas, I'm sorry. Capital lambda times the sum of lambda j bigger than 0 has to be balanced by little lambda times the sum of lambda j's less or equal than 0. Okay. So in some sense, you are taking the most, among all solutions, you are taking the most concave one, the one that has the largest possible negative eigenvalues with respect to the negative eigenvalues with respect to the positive ones. Another example is Monge-Ampere equation. Monge-Ampere equation is an extremal. If you want to solve, find a convex function or you tell me find a convex function u such that the determinant of the square of u is equal to 1, right? This is the extremal, this is the infimum among, so u0 satisfies that the infimum, the sup of aij, I always get confused, the infimum. So as I take all the possible equations you can cook up, aij, dij of u equal to 1, where you ask the matrix aij to be non-negative and such that the determinant is 1. Okay. So if you take all possible equations of this form, if you want to get the smallest, the smallest possible number, you have to mirror the dij, uij. You have to take the minors of dij, uij. Okay. So any solution of an equation like this with determinant aij equal to 1 is a super solution of a Monge-Ampere equation. I mean, maybe 1 or 1 over n, some constant. Okay. So the problem, the remarkable thing about the theory is that I ask you, to solve that problem, I ask you to find a function, this crazy function, right? And the remarkable thing is that that function exists, and you first prove that there is in a very weak fashion using Perron's method, and you end up proving at the end of the day that the function is C2 alpha, and therefore this relation it satisfies at every point in the classical way. Okay. So how can you guess, or how can you see that you end up with some regularity? Okay. So let's do a little bit of formal computation. So you have f of the square of u equal to 0, let's say. Okay, this is going to be a fully nonlinear equation. If you take a supremum of elliptic operators, right, it's also elliptic. What does it mean, elliptic, right? So what does it mean that aij, how can I say that aij, dij of u is elliptic without talking about the matrix? So I want to say aij dij of u, right, is elliptic. In other words, the matrix aij is positive, but I want to say it without talking about the matrix, right? So I say, okay, what is this? This is an L of matrices M, an operation on matrices M. You give me a matrix and I get you a number, right? So this is L, let me call it L sub A of M, right? So I say that A is just elliptic, that is that aij is positive, simply means that this is monotone as the function of a matrix, right? In other words, I'm not talking about aij, I'm just saying L of A satisfies that if n is a positive matrix, then LA of m plus n has to be bigger or equal than LA of m. Okay? And in this is implicit the comparison principle, because if you have two solutions, two functions u, and one touches another from above, then the quadratic part of v is bigger or equal than the quadratic part of u. So LA of the square of b philosophically is bigger or equal than LA of a square of u, and so they cannot satisfy the same equation, right? I mean, they can satisfy it, but you can try to go around it, okay? If you want to say that it's uniformly elliptic, right, that is, if you want to say that aij is between lambda the identity and lambda the identity, you can say it by saying that if you take a matrix n, which is n1 plus n2, both or minus n2, both positive, right? And n1 is a small multiple of n2 is a small multiple of n1, right? In some sense, the largest eigenvalue, let's say, for both, right? I mean, take or give a constant depending on dimension. Then, when I put here the difference, I still get positive, because the positive part will make it increase proportional to the largest eigenvalue of n1 times the smallest eigenvalue of aij, at least, right? And the negative part is going to make it decrease as at most, the largest eigenvalue of aij times the largest eigenvalue of n, right? So if this ratio, the ratio between eigenvalues, is big enough, then this function is still monotone. Okay? So this is a definition we can give for f of d squared. We can say that the equation f of d squared of u is uniformly elliptic if f of n plus n for n positive is smaller or equal than f of m plus a large multiple of the norm of m, that is the maximum eigenvalue, let's say, and is bigger or equal than f of m plus a small multiple of the norm of m. Okay. This is the same as what I'm saying here in a different form. Okay. So in particular, this implies that if I want to think of the equation f of d squared of u equal to 0 as a surface in the space of matrices. So we can think of the equation, to understand the geometry of the equation, and ellipticity means that this surface, right, is a graph of a surface in the direction of any positive matrix. That is, if you give me any matrix M0, this monotonicity means that S is a graph. I mean, let me normalize f of this square, f of 0 to be 0. So it's a surface through the origin. Okay. So ellipticity means that S is a graph in the direction of any positive matrix. That if I take any matrix M0 and I do M0 plus Tn, this is negative if T is negative enough. Okay. Positive for large T, and at some intermediate value, T becomes 0. So there is one value for which this matrix belongs to S. Okay. In fact, uniform ellipticity, in fact, means that this is still a graph in the direction that is a positive direction plus a small negative direction. Okay. So uniform ellipticity implies that S is a graph in the direction of n1 minus n2, provided n2 is a small multiple of n1, provided that the largest eigenvalue of n2 is a small multiple of the largest eigenvalue of n1, which means that S is a Lipschitz surface. Okay, if you take the direction of x squared, for instance, the direction of the identity, S is a Lipschitz surface. Okay. If you assume that f is differentiable, right, then if you take the derivative with respect to t of f of the square of t plus f of m squared plus t, you get fij times nij. Right? If you assume that f of the square of u is differentiable, right, then you can take the derivative of f of m0 plus tn with respect to t. Right? And this is fij times evaluated at m0. Let's take the derivative at t equal to 0 times nij. And so we know that for any strictly positive matrix, this is strictly positive. So that means that this is an elliptic matrix Aij. Okay. Which brings me to the discussion of why do you expect regularity for solutions of this equation? And so we go to Serring's advice is take a derivative because it's an equation which is invariant under translations, right? So you take a derivative to see what equation is satisfied by the first derivative of u. So you take the derivative of f with respect to the ij position. And then you take let's say you take a directional derivative in the direction E, right? And then you take, then they have to take the E derivative of dij of u. So you get dij of dE of u. But at this point, you don't know anything about u. I mean, if by now you know that u is C2, then you don't need to worry about the first derivatives, right? So at this point, if you have some weak solution somewhere, you want to make sense of this, and so you say, okay, if I can make sense of this, then this function w satisfies an equation aij dij of w equal to 0, where I don't know anything about these aij's except that they are an elliptic matrix. And so the Harnack inequality says that if w I know that is bounded, the w is Helder continuous. And if I know that I don't know that is bounded, I can have some hope, because there is when whatever is a derivative has some sort of implicit bound on it, right? It is that its integral is bounded. You know, w is a derivative, and so if u is bounded, sort of, in some sense, there is some hope. So basically, this says that if you have a solution of f of d squared of u equal to 0, then you, in some generalized sense, you can go for C1 alpha. I mean, you can try to prove that such a solution has a Helder continuous first derivative. Oh, this is a theorem. I'll say in a minute what is the weak solution that you can prove. I mean, you can prove existence of a solution that at the beginning is weak, and you end up proving that it's C1 alpha. But U doesn't see linear functions. See, Serring's advice was for divergence equations, but U doesn't see linear functions. So one may hope that second derivatives also satisfy something. And so you do DEE. When you do DE, you have a second equation, an equation for DE of U, right? Just by putting the derivative here. So you get Fij DEE of U, and that's nice. But you have the problem that you have to put here the derivative also here, right? So you get plus the derivative of Fij with respect to the KL position, and then you have dKL of the E of U dij of the E of U. And in principle, this looks very bad, but at least this thing has the structure of vector matrix vector, right? This is a vector in n Rn times n. This is the same vector in Rn times n in the ij and kl indices. And this is a matrix in Rn squared times n squared, right? So he has the structure vector transpose times m times vector. And so if the matrix is positive, then this has a sign. That is the case when V is just the supremum of a family of operators. Because when you have something which is a supremum of a family of linear functions, it's convex. So f is a convex function in the space of matrices. Okay. So if f is a convex function in the space of matrix, these are the Hamilton-Jacobi-Bellman equations. This Monge-Ampere is concave, Monge-Ampere to the 1 over n is concave on the space of matrix. If f is concave or convex, right, then this term has a sign. It's positive or negative, but it has a sign, which means that all pure second derivatives are subsolution of an equation with bounded measurable coefficients. Okay. So d of u okay, equation with bounded measurable coefficients. If you look at the proof of Krylov and Safanov, some solutions do not satisfy the Harnack inequality. Okay, it's not good. But at least they have an important property. So suppose you have a subsolution, right? So important property of subsolutions. This is also true for this part of the Di Giorgi proof of the regularity of solutions in divergence form. It's a general statement. That is, if you have a subsolution, let's say, which is less than 0, for instance, so it's below 0, and it is less than -1 in a non-trivial set in measure, then in half the cube it has to come down. So in half the cube cannot stick to the top. In other words, you cannot have a subsolution which goes down a lot and nevertheless manages to stick on the top all the time. For harmonic functions, it just follows from the mean value theorem, right? If you have a harmonic function which is a subharmonic function, which is smaller or equal than 0, and it is less than -1 in a non-trivial chunk from the mean value 0, the function is smaller than strictly smaller than 0 inside, because the function here is less than the average in a ball grabbing this piece. Okay. So for the general theorem, it's much more there. It's a substantial part of their proof. And so this is the idea behind the theorem proven by Krylov and Evans independently that says that if the equation is concave or convex, then it's C1 alpha. So if that is, if all the second derivatives are sub or super solutions, then U is C2 alpha. That's the case of the Monjan pair. That's the case of Krylov's operator. Heuristically, the reason is that suppose that your function has bounded second derivatives. Okay. So that means that f of the square of u for your solution lives on the surface S inside the ball. Okay. In other words, the d square of u is spread all over here. But then the square of u has to be in some part of the surface in a non-trivial set of the x variables, right? You have the x variables here, and for each point you have that d square of u is living in the surface S. But there must be in some non-trivial set here, right, where the d square is concentrated somewhere, right? I mean, if you split this in many little pieces, there must be one of the little pieces that covers here a good chunk. So let's say here. Okay. Then you can choose a d square, which is here like of order 1 and here much smaller. And the fact that it is a that DEE is a sub-solution means that in a smaller ball it's going to push this away from its maximum. So it reduces the size of the ball. And so if you repeat that again and again and again, you end up that the image of the square of u decreases. It's not important that this surface is concave or convex, which also follows from the convexity or concavity of f. What is important is that on one side, all of the second derivatives are sub-solutions, and put together, they satisfy an equation. They live in this nice elliptic surface. Okay, so the bottom line is that if you start with weak solutions, of f of the square of u, if f of the square of u is not convex, it's just elliptic, then solutions are C1 alpha. There is a counterexample of Nasirashvili and some collaborator that there are solutions which are C1-1 and not better. But if your solution is, if your function f of the matrix d square is concave or convex, then solutions are classical, which is the case of the Puch extremal operator, for instance, which is a supremum of linear operators. Let me point out about the Harnack inequality. Okay, so let me recapitulate. Then we have an equation. I'm going to look at equations f of d square of u uniformly elliptic. You can put f of d square of u and x And I won't go through it, but you can recuperate all of the Schauder estimates or whatever. You can go as far as the operator without the x goes. In other words, if you put here an x which is, let's say, Helder continuous or even bounded, and this is not concave, you cannot go beyond C1 alpha, but you can go all the way to C1 alpha. Okay, so you can do, if dependence in x is, let's say, C alpha, then A, we have U is C1 alpha if F is general, B U is C2 alpha, bounded solutions U, C2 alpha if F is concave or convex. And what I mean by this is, if you have a function, the solution U, if U is a weak viscosity solution in the unit ball of Rn and is bounded, then it is regular in half the ball. Then it is regular in B1 half. Okay. So you can construct your solutions by the Perron method, by whatever. You get a weak viscosity, a continuous function that is a viscosity solution in the sense that you can compare with polynomials. Okay. And then you get that thing. As soon as you go inside the ball of radius 1, it becomes regular. The other point I want to make is a Harnack inequality does not guarantee that much regularity. The Harnack inequality only guarantees Helder regularity. And also there are counterexamples in the literature. Several famous, Safanov and Nasdirashvili, I think, both of them have. But it has Harnack inequality, it has, on the other hand, an important concept, which is like control by below implies control by above. In other words, if you have Harnack inequality and the function has any, at a point, has any modulus of continuity by below, for instance, if at a point I have this graph of a solution Aij and it's only Helder continuous, but if at a point, let's say here, I can touch it with something that has some modulus of continuity, then the solution reproduces the same modulus from above. Okay. The Harnack inequality, so this is up to first derivatives. And the reason is the following. Suppose that you have a point x0, the origin, right? And we have a solution U, right? Solution of L of U equal to 0, let's say, so it satisfies the Harnack inequality. Divergence or non-divergence, this is true for both. And suppose that U has a modulus of continuity by below. What do I mean? I mean that the inf of U in the ball of radius R center at 0 is bigger or equal than some modulus minus gamma of R. That could be R to the alpha or R log of R, your favorite function gamma. Okay. Then it also has it by above. And this is trivial. All you do is you take the ball of radius R, and in the ball of radius R, if you subtract its constant, the constant gamma of R, U plus gamma of R becomes positive. In other words, if I make this my zero line, this graph becomes positive. And the Harnack inequality says that in half the ball cannot go more than twice above, right? The Harnack inequality for this being the zero line, then and this being one height, let's say, right, by renormalization, says that the solution cannot go up more than a multiple of what it goes down. So if you do that at every scale, you reproduce exactly the modulus of continuity from above that you have from below. If you, on top of it, your function doesn't see linear functions, your equation doesn't see linear functions, right? Then you can subtract, then you can go one more derivative. In other words, you can subtract the linear part, and then here you may have anything that you have below quadratic, you can reproduce above. Okay. So for equations of second order, non-linear or linear with bounded measurable coefficients, regularity by below implies the same regularity by above. Exactly the same regularity by above. So if U satisfies f of the square of ux equal to 0, and this can be bounded measurable coefficient dependence in x, right, or linear, 0, then if U has a modulus of continuity by below all the way to C11, for instance, if it has a paraboloid tangent by below at a point, then it has a tangent paraboloid by above with an opening, a multiple of the one below. And then it reproduces it. Okay. This is what we were saying the other day about the richness of the viscosity method, right? The fact that the notion of viscosity says that if you have a tangent paraboloid from above, in some sense, the function is also nice by below. This is implicit. If you put the Harnack inequality, it's implicit there, right? So let me say 2 words about it. So the viscosity method says, I want to say that f of the square of u and x, let me assume continuity in x, right, is equal to f of x. And I want to say it for a function which is continuous only. Right? Okay. And the idea was, okay, I cannot talk about the square of this function, but what I can say is that I want to say that if this happens, right, and I happen to have at the point x0 a quadratic polynomial that touches it by above, let me make it a quadratic polynomial that touches it by above, right? The quadratic, when I plug here the quadratic polynomial, I have to have a bigger right-hand side, right? This was the monotonicity, the notion of ellipticity of f. If I put here a bigger d squared, I have to get a bigger right-hand side. Okay. So I'm going to say that u, the continuous function, is a solution, or a, let's say, is a sub-solution first, right? One side and one side. If whenever I put here something that I can compute, and the simplest thing is a quadratic polynomial, and the quadratic polynomial happens to touch the surface by above, I have to get a bigger number. For any p. Zero. I must get a bigger number. This f of d square of p x has to be and if I touch it by below, I have to get a smaller number. So I'm now, you see, this is what is reasonable. So now you invert the reasoning and you say, okay, now let's do it the other way around. I take a function u that is continuous. And I don't ask that any polynomial touches anywhere. I don't care. It's a continuous can have a lot of wiggles. Maybe a polynomial touches a very few points, right? I don't care. I'm not asking that. But I said, if by any chance at a point I can touch my solution, my function u, with a polynomial by above, the polynomial should be forced to have this inequality. And if I touch it by below, the polynomial should be forced to have the opposite inequality. Right? So I'm basically saying almost nothing of u. And so, I say, when you see this definition, say, okay, everybody has the right to write the definition. And so the remarkable thing is that you build by the Perron method, it's easy to build a continuous function that satisfies this. Right? You take the inf of all continuous super solutions, right? And so naturally inherits this property. Okay, these two properties. So it's easy to construct by the Perron method a viscosity solution of an equation like this if this equation is uniformly elliptic in d square of u and continuous in x. Okay. And the remarkable thing is that you end up showing that the object you constructed is a classical solution. Okay. Okay. Okay, let me stop here, and then next hour I do the periodic, I discuss the periodic and random homogenization. So let me try to discuss now the problem of homogenization of fully nonlinear equations. Okay, and so let me start by making sort of some heuristic discussion for the periodic case, and then I'll do the ergodic case. Random ergodic case. So the periodic case was worked out by Evans, but let me sort of discuss it in this context. Okay. So the idea is the following. So what you are given is a family. You are given the equation f of d square of u and x equal to 0, right? And x, this is an equation, it's uniformly elliptic and periodic in x. Okay. In x. Right? For instance, you can think of a of x lambda plus lambda minus equal to 0, where a of x is 1 plus cosine, no, 2 plus cosine of x. Right? Okay, and then you look. So as we discussed in the general case, you look at you shrink. You look from far away to your the underlying structure x, right? In other words, you look at solutions. Right, so you have a periodic configuration, right, where the equation changes in each square periodically, and you want to look from far away, and you expect that what you will see will be an equation, a solution of an equation. In other words, that there will be a particular equation, which is the limit of the equations, and so the limits of the u epsilon, if you do a Dirichlet problem, will converge to a solution of the solution of the Dirichlet problem for the limiting equation. Okay, so in other words, you want to look, you want to shrink the oscillations. In other words, you want to look at f of d squared of u of x over epsilon, right? That means that now when x is epsilon is like when before x was 1. So that means that you have reduced this structure to a very fine grid of size epsilon, right? And you are looking at a fixed domain D, for instance, and you can look at the Dirichlet problem, right? So you can say, okay, for every epsilon, let's find the solution u epsilon of f of d squared of u epsilon x over epsilon equal to 0, right, with the fixed data for all of them, u epsilon restricted to boundary of omega equal phi of x. Okay, and these are all Helder continuous functions because they all satisfy the Harnack inequality, right? We said any solution of an equation like this is an equation that you can write in non-divergence as a bounded measurable coefficient equation. So any solution of this equation is uniformly Helder continuous, so it has to converge to subsequence. Every subsequence has a convergent subsequence, right? And so what you want to show that is all of them converge to a single function u0, right? A solution of some equation f of d squared of u0 equal to 0, and that if f bar inherits the properties of f, like if f happens to be continuous, happens to be concave or convex or whatever, this is inherited by the limit. Okay. And so what are you going to do to prove that? Well, suppose that you have the solution u0 of that problem, right? Or you have the limit of some subsequence u0, right? So suppose that you take, okay, let's take the limit. They are all Helder continuous, so there is some subsequence u epsilon k that converges to a function u0, right? And let's assume that f is convex for the moment. So solutions are C2 alpha, right? So it's a very nice u0. Suppose you know that u0 is a solution of a convex equation, or you want to prove that u0 is a solution of a convex equation. So you said, okay, I'm going to take a polynomial p, right? I'm going to touch u0 by below, and I want to see that I am forcing the polynomial to be special, right? So I'm going to take a polynomial, I'm going to look, I want to show that f bar of d squared of p, right, is bigger than 0. Okay. Now, how do I do that? Well, what I can try is to build a corrector for p. In other words, I have the p, right? And since I'm doing this epsilon scaling, right, if I have a corrector for p at level 1, since the natural scaling here is 1 over lambda squared u of lambda x, I suppose that I have the polynomial p now in all of Rn, right? And I can find a corrector. What does it mean, a corrector? Will mean a periodic W, find for p a corrector, right? What will be a corrector? Will be to find the polynomial-like solution of the oscillatory problem, right? That was what the correctors were. Take the linear function, you take the linear-like solution of the oscillatory problem. In other words, you want to find, let's say, a bounded W, right, such that P plus W is a solution of f of d square of h x equal to 0. Okay. If I find this is very close to the polynomial, right? Polynomial is quadratic, it's growing enormously. This stays at distance 1 from the polynomial. So it's like a polynomial-like solution, right? Referring to the plane-like solution of the minimal surfaces. So I will have a polynomial-like solution, right? What happens when I go to the epsilon problem? Well, to keep a polynomial, right, I have to do the scaling h So how do we go? Go from scale 1 to scale epsilon. Well, the natural scaling is lambda is to do h of Rx 1 over R squared, right? That allows you to look at h far away. So R, if I want to do epsilon, I do h of x over epsilon squared, right? The d square of this is the same as the d square of h, right? But now I'm evaluating it at x over epsilon, right? So if I want to pass from something of scale 1 to scale epsilon, I have to do this family of transformation. This family of transformation keeps the p the same, right, which is what I want, and the w becomes epsilon squared w of x over epsilon. So the w is very, very tiny, right? The w becomes, w was bounded, so although it's very oscillatory, right, because you are evaluating it far away, but it's epsilon squared high, so it's great.
Why doesn't P not scale?
Well, b is epsilon squared. It's quadratic. Yeah. This is the quadratic part what matters. It's pure quadratic, because the linear functions, this problem never sees. Okay? So that means that, so that gives me sort of a very nice corrector of the polynomial at this level. So I say if I can touch P, right? If I can touch the limit with P, right? Adding this little wiggle, right? I can add this little wiggle, move it a little bit, and I will be touching the approximating function u epsilon, right? In other words, the u epsilon is something which is very close because it's convergent. So if I touch P, I add the little wiggle, I move around, and I touch the approximating function. Okay? And so if I manage to touch the approximating function, this polynomial P better be a subsolution of the limiting equation, because if not, I'm doomed. This is not a limiting equation for u0. The only way I can say that u0 satisfies the limiting equation is that this happens. Okay? So that means that so if we go back to the idea that to prescribe an elliptic equation is to prescribe an elliptic surface in the space of matrices, right? Then what I have to find is what is the surface f bar d square of P. In other words, I have to find a way to say which P's have to be super solutions and which P's have to be sub-solutions of the limiting equation. Sort of if I give you the long list of all the P's which are super or sub-solutions, I am describing for you the equation f bar of the square of P, of the square of W. Okay? So in some sense now, at the difference with the divergence, in the divergence case, any linear function had its corrector, and the corrector told you what was the effective energy. In the non-divergence problems, it's the other way around. In other words, I'd like to see the non-divergence problem as being characterized by sort of global profiles. Right? If you give me the equation f of d square of u equal to 0, right? This is characterized by which quadratic polynomials are solutions of the equations. If you give me a free boundary problem where you want u to be harmonic, and when it hits 0, u nu is equal to 1, this is characterized by the global functions which are half a plane with a slope 1. Okay, and when you do the viscosity method, when you do comparison method, then what you have to know is what are, for homogenization, what are the global profiles that characterize the problem, okay, the limiting problem. So we have to decide, so in some sense, so what is implicit here is that to find a corrector, I cannot put any polynomial and find a corrector. If I put the polynomial x squared, right, if I put the polynomial f squared, f of x squared, right, if you give me the polynomial x squared, then m is the identity. Right, so suppose you tell me, okay, let's find the corrector for x squared. Right, then what do I have to do? I have to find f of 2 times the identity plus w x equal to 0, the square of w, right? Okay. But for this being b equal to 0, then this square of, let's suppose that the ellipticity of the operator is lambda, right? Lambda. And I want to find lambda x squared. So here I have a lambda, right? Then you can check that then the d square of w has to be negative. Okay? So if the square of w is negative, that means that w is convex, with a negative d square, is never going to be a corrector which stays of size 1. When I try to construct it, it's going to go to plus infinity. If I put minus x squared, w will be concave or the other way around. So obviously I cannot construct a corrector for every quadratic polynomial. In other words, to construct a corrector, right? In fact, let's do that. Let's say, okay, suppose I want to construct a corrector, right, for m plus tn. So let's take n a positive matrix and try to construct a corrector for m plus tn. In other words, a w such as this plus d squared w, right, equals 0. Okay? If we take derivative, so this is wt, a corrector for each given t. Right? If I take the t derivative of this, let's say at m equal to 0, I have f of fij of m, right, times dij of dt of w sub t equal to 0. Let's see, what am I doing? I'm doing something wrong. Taking the derivative of this, so I get fij, okay, fij of m plus d squared wt times n, plus d squared of dt of w equal to 0, okay? Nij. I'm taking the derivative in t here and here, right? Now, if n is a positive matrix and the operator is elliptic, this is a positive constant, right? So that means that the right-hand side of this equation for dt of w is always positive. Okay? In other words, this means that fij d squared of dt of w sub t, right, is positive. Which means that it's above, it's positive, it is below a multiple of x squared, right? You always use x squared as an upper barrier for this. Okay, if you have an equation is positive, no, it's negative, okay, sorry, it's negative. So that means that the corrector is always above a polynomial like this, right? Because a polynomial like this, minus constant minus epsilon x squared, right, is a subsolution of this equation. Okay, if I put epsilon squared, I get a subsolution of this equation. Okay, so that means that there is only one t, exactly one t for d for which this has a chance of being a corrector. Okay, because when I do derivative in t, if I do the w for one of the functions, right, and I do the derivative in t, this is growing quadratically. So the function is growing with constant speed here, proportional to a quadratic polynomial. When I try to do the correctors are or too big above or too small below. Okay? So that means that if I take this, there is only one t. I have a chance only for one t to get a corrector. Because as soon as I enlarge it a little bit, the w is going to grow proportional with speed proportional to t above. Okay? Because the w sub t is always like a quadratic polynomial, bigger than a quadratic polynomial. Okay? So that means that here the corrector is really a compatibility condition on the polynomial. So the corrector tells you, if you have a corrector, that tells you that that polynomial is a candidate to be a solution of the limiting equation. And you are getting one for each direction, so that looks good because that means that this will describe for you the homogenization surface. Okay? So how can you construct a corrector? How can you show that there is a corrector? You see, the problem is that it may never be a corrector, right? It may be, right, you have sort of its basic profile for W, which is like this, right? And then when you move the t, this part grows and this part decreases, right? So for t very large, the thing will end up being like that. For t very small, the things will be very like that, and will never align along this line, right? Okay. So let me propose the following. Let me propose to do what we did with the minimal surfaces and constrain W to remain positive. Okay. So what do I mean by that? I mean, let's look at the equation f of m plus d square of w x. Okay, let me put temporally equal to 0, right? Let's take a very large cube, right? And instead of solving this that can go up and down, let's take the least super solution above 0. Right? In other words, you do the Perron method to construct W, you will do that. You will take all super solutions and you will take the smallest of them. So I said, okay, I'm going to do the Perron method. I'm going to take all super solutions. But when I try to go through 0, I'm going to stop there. Okay? So I said, let's construct U0 the least super solution. Smaller or equal than 0. Sorry. Above W equal to 0. Okay. This is a classic tool. This is called the obstacle problem. In other words, where you want to find among all you start the Perron method, but you are not allowed to go through u equal to 0. Okay. So u0 is the solution, w0, sorry, of the obstacle problem. Okay. And believe me, okay, I'll prove it in fact in a little while, that the solution of the obstacle problem is very regular. It separates from 0 quadratically. Even if you have an equation with bounded measurable coefficients, the solution of the obstacle problem separates from the obstacle quadratically in a universal fashion. So believe for a moment, it's not hard to prove. I'll prove it in a minute. So u0 separates. So what are the properties of u0? Okay, the first property is that u0 is a super solution. The smallest of a family of super solutions is a super solution. u0 is a super solution. W0, I'm sorry. The second is that when it doesn't touch the obstacle, it's a solution, because there is free, it's the Perron method, right? The least super solution is a solution. If not, you can lower it a little bit more. So when u0 is positive, so in some sense, right, and you are trying to do, when you are doing this, what happens with the corrector? The corrector goes up and hits down, and goes up and hits down, and goes up and hits down, and hits down a lot of times. I mean, this is not right, but this is the problem you have that starts to hitting down all the time. Okay? This is what could happen. And the third thing that I'm going to prove for you in a second is that W0 separates from 0 quadratically. Okay. So now let's seek that compatibility condition. How do we seek the compatibility condition? Let me put here m plus t the identity, right? That is like adding x squared. M is the d squared of a polynomial, and this is the d squared of the polynomial plus tx squared over 2. Okay? And when t is very large, right? When t is very large, to be able to make this equal to 0, the d squared of w will have to become very negative. Right? So w will be very concave. And most probably will touch very little the obstacle. It may touch over here somewhere, but it's going to lift immediately and it's going to be very concave. While if t is very negative, this matrix is very negative. To make a solution of the equation, the square of w has to sort of be positive, right? It has to have larger positive eigenvalues. Okay? So in some sense that this, so w will try to be very convex, but cannot go through 0. So it's going to stick a lot. Now we are in the periodic case, so things are much simpler, because now I say there is a critical T0 for which one square gets clean. Right? Let's take the period, and for T large, you are far above. There are many clean periods right now. Let's think of this now in the plane, in a large cube or in a large ball. Right? And for T very small, large, W is above here. There are many clean periods. Periods have size 1, and we are talking in a large cube M, right? So there is a critical T0 such that I have one clean period. What do I mean by one clean period? I mean that the solution of the obstacle problem becomes positive in a full period. Okay? So that means if this is the first time the solution of the obstacle problem becomes clean in a full period, that means that here the corresponding W is very small. It's sticking in all the period. In at most 2 periods, it touches the bottom and has quadratic growth, right? So since it's the first time that it touches the period and this process is continuous, means that at this point the W touches the top still in many bottom in many places, right? But it's very small. It's of order 1 because in each period touches the bottom basically. Take or give a period or 2. Okay. Now I take any larger cube. So now I said, okay, now let's take this cube and draw it little. Okay. So this has a size capital L, be very large. But let's put it in a much larger cube. Then an important property of the solution of the obstacle problem is that it is monotone. Right? Because any non-negative super solution that lives in this large cube, when I restrict it, becomes admissible for this one. So any non-negative, if Q1 is contained in Q2, any non-negative super solution defined in all of Q2 is admissible for Q1. Defining Q2 is defining Q1, is non-negative. It is one of the many for which we are taking the minimum. We are taking the least super solution. Okay. So the one here is above the one here. The one here has a little clean cube. So the one above has this little clean cube. But I can move this all around. So that means that the one above is completely clean away from the bottom, except when I have to cross here. So except this strip. Right? I mean, I have in 1D, right? I have the solution in this cube, and I know that here there is a little period where it makes a blip, right? And so I said, okay, the solution for this long line also makes a blip here because it's above. But I can put it here. And so I have a blip here. So the solution of the long domain also has above here. In fact, I can move it along all the cubes. So that means that the solution above is above it's a free solution all over. See, this is like the Birkhoff condition for the minimal surfaces, where we found a clean cube, and from the Birkhoff condition, translation condition, we got a clean cube everywhere. Okay. So that means that, except here, when I cannot cross anymore, I get stuck, right? But except here, in most of the cube, I'm going to be above 0. So this really starts to look like a corrector. So you take longer and longer domains, and you take the first T0, for which you get a clean cube. Okay, that T0 is decreasing, because the T0 which was good for one cube is good for any bigger one. So it's a sequence of decreasing T0s, and that gives you the corrector. Okay. So let me try to now explain the ergodic situation, because the pictures are pretty much like this one. So in the ergodic situation, what you have, right, is a bunch of operators. In other words, you have a bunch. Suppose that you have a medium, and the medium sort of has been deformed by some process. Tracks go along. You make a road, and the tracks go around when the concrete is fresh, right? And so the medium is not anymore the nice plane, right? So you have a bunch of possible deformation of your mediums, right? And so sort of you can think that you close your eyes and put your hand. You have the set of take the set of, let's say, all possible second order equations with the coefficient x, Lipschitz, right? So let's look at all possible equations you can dream of, right, with a coefficient x, right, which has some ellipticity, right, little lambda and capital lambda, right? And you close your eyes and you put your hands and you get one of those. Okay. So you get one of those. You may say so you get one of those, and you want to get it with some frequency. 10% of the time you get this operator. 20% of the time you get another one. Okay. So in some sense, you have among all operators, right? You have in the set of, let's think in the set of all operators, you have some sort of probability, which is the density with which you will see this given medium. Okay. So let me write this as saying that there is that this equation appears with with some density omega living in a probability space. Okay. So you have this omega lives in, you can think of all possible equations, right? Omega in a probability space M with a probability density mu. Okay. But you have this process, and this process has several properties. For instance, it's translation invariant. Suppose that if you can find this equation with some probability looking here, if you look somewhere else, you find that equation with the same probability. Okay. In other words, so you have for any omega in a probability space, you have an equation, right? And if you translate, right? So if you look at f, so the equation f of the square of u x plus y, right? It also appears in your family of possible configurations, right? And it appears with the same probability than this one. Okay. So the square of u of x plus y appears again, corresponds to a different omega right now. In other words, when you see this, right, the translator, if I stand them here and I see the translation, right, it appears will not be for the same omega. For that omega is that equation. So let me call that tau sub y of omega, right, the translation of omega to sub y. And what you ask is that the frequency which this appear is the same as the frequency which that one appeared. Okay, in other words, you ask this tau sub y to be measure preserving. It appears with the same frequency. So you have this translation invariant property, as you are going to see the equations. Sort of, if you open a square and you see the equations restricted to the square, it's going to look exactly as if you open another square and you see the equations in the other square. You will see the equations with the same frequency, although they may be different in one or the other. Okay. So in other words, I like to look at the problem, think of the problem this way. So you look here and you look here, right, and you look here. And if you just see this one, you see the same family of equations with the same probability. Okay, but the way they are connected is what is different. So if you open this and this, then the way that one equation is connected with the other is still translation invariant, right? But it's not independent. There is correlations. Okay, so it's like having a family of probabilities in larger and larger domains with some compatibility conditions. In other words, each one is the same, each two pairs is the same, but if you look at the probability of seeing an equation which is here in the set S and here in the set S prime, this is sort of a joint probability, and it is given to you. And so what is important is that you have these equations, it's translation invariant, and that they mix some way. Okay, in other words, that you don't find the same operator in all the places all the time, right? That if you start to mix that you will have an operator here is mixing with an operator different here, an operator different here, and so on. Okay, which you state by saying that if you take a set of measure less than 1 and you start to translate it, the intersection of all the translations, the probability goes to 0. Okay, in other words, you cannot stay on the same set again and again and again and again. Okay. And so we want to show that if you have, if you rescale by epsilon, now we want to show that if you rescale by an epsilon, in other words, if you look, so you have again your basic grid, but now the things are not periodic anymore. You scale by epsilon. Right, so you look at the little grid and you look at the solutions of the Dirichlet problem in this domain. You want to show that as epsilon goes to 0, the solutions of this equation will converge with probability 1 to a solution of a fully nonlinear equation where the x and the omega have disappeared. Okay, so it's the same as in the periodic case. So we want to see that epsilon goes to 0. Converges to a u such that that you satisfies a fully nonlinear equation. Okay. And so basically the problematic here is the same as the problematic with periodic coefficients. In other words, you have to decide which polynomials will qualify. This, again, all of these functions are Helder continuous because they are solutions of equations with bounded measurable coefficients. They converge to something, and you want to show that the something is a solution of the fully nonlinear equation. Okay, and so it's the same problematic as before. You want to say, if I touch a limit with a quadratic polynomial, what can I say about that quadratic polynomial? And the idea is then that that quadratic polynomial, right, in some sense, can be corrected to a solution of the epsilon problem. Okay. So we have the problem, the same problem as before, like with the correctors. You take the quadratic polynomial p, right, and you say, I'm going to solve. You try to solve the epsilon, or the, if you take a, you can work in a cube 1 and size epsilon, or in a cube 1 over epsilon and size 1. Okay, let me do it in a cube 1 at size epsilon, and then I'm going to change. Okay, so I say I have the polynomial cube of in the cube of size 1. I'm going to solve the equation f of d squared of u epsilon x equals 0, right, with the same data as this polynomial. And if it were a corrector, that means the solution is going to run very close to the polynomial, right? So here I said, okay, we don't need such much as a corrector. We need, if at epsilon goes to 0, will it be the case that the solution u epsilon will align to the polynomial? Okay. And as I take epsilon smaller and smaller, I just solve and see what happens, right? And 3 things can happen, right? Or 4, whatever. One possibility is that as I solve this with epsilon smaller and smaller, the solution starts to be above, more and more above my polynomial, right? And that's great because that is telling me that I have to qualify the polynomial as a sub-solution because it's more concave, more convex than the solutions. It will only be able to touch the limit from above, right? So if u epsilon happens to align, so to separate upwards, then I'm okay. If u epsilon separates downwards, right, then this has to be a super solution. The limit in the polynomial qualifies as a super solution because can only touch the solution by below. Right? I can only touch this wiggle if I lower the polynomial and I raise it and I touch here. Okay? So the problem is, like it happened with the correctors in the periodic case, that it may not align. That is that the solutions will be above for a while and below for another while. Okay, and if the solutions do not align, that means that there is no homogenization limit. Okay, so I have to see if I do have this duality that the solutions align by above or below. Okay. And in an ergodic context, there is one theorem, right? It says that is that if you have a subadditive quantity in larger and larger cubes, it has a limit. Okay. So the main property I'm going to use suppose I take the origin, and for any cube in the origin I define a quantity. So for any cube QR, right, and for any omega, right, QR of 0, right, I define a quantity d or sigma of QR and W. Okay. And in fact, I define it in all cubes in such a way that it's translation invariant. In other words, that sigma of QR and QR of 0 and W is equal to sigma of QR of Y and tau of minus Y of W. Okay? Okay? So suppose I have a quantity which is translation invariant in this sense, the same way that the operators were, right? Suppose that sigma of QR is of order QR. Well, it's bounded above, let's say. In my case, it's going to be smaller or equal than 1. Okay. And suppose that it's subadditive. In other words, suppose that if I take a cube and I divide it in a bunch of subcubes, then the Q sigma of the union, right, is smaller or equal than the sum of the sigmas. Okay. So let's say this quantity is, let's make it positive. 0 less than constant. Then as r goes to infinity, sigma of QR over QR has a limit, lambda, a unique limit lambda independent of omega. Surely to some quantity lambda over, I'm going to QR sigma. Okay. This is the mix is makes the limit unique. So this is ready for the obstacle problem, right? In other words, I want to see if the U's are going to align, you give me a polynomial, if they are going to align to the polynomial above or below. Okay? And so what I'm going to do is I'm going to, instead of taking the free solution that oscillates, I'm going to take the solution of the obstacle problem. In other words, you give me the polynomial, now let me go, since this theorem is written for larger and larger cubes, now let me go to the large scale. In other words, now let me make epsilon equal to 1, right? And so I take a polynomial p, which is a large quadratic function in large cubes, okay? So let me take a polynomial, you give me a polynomial p, so you give me a polynomial p in a large domain, in a large cube QR. So now the scale of oscillation is of order 1, right? And I'm going to look at U sub q omega p, whatever, right? We're going to be the solution to the obstacle problem. That is, U is going to be the least super solution of f of d squared of u x omega, okay, above p. Okay, so it's going to be an object like that, may touch somewhere, keep up, may touch somewhere, keep up, and so on. Okay. And I want to decide if, when as epsilon goes to 0, this is going to align or not to the polynomial, or below or above. Okay, and so the ergodic quantity I'm going to take is the measure of the contact set. Okay, so D. Okay, let me say a couple of them already say the basic things about the solution of the obstacle problem. It's smooth when it doesn't touch the polynomial, satisfies the equation. It's a super solution across. Okay, and so let me say a couple of things that have to do with the alignment. Okay, this is the following. The first question one may ask is okay, the quantity I'm going to take as the ergodic quantity sigma of omega and q is going to be the measure of the contact set. Right? As we saw in the periodic case, if I take a large cube, right, and I decompose it in subcubes, and I take the measure of the contacts here, the contact set of the solution in each one of these cubes contains always the contact set in the larger one, because the solution of the larger problem was above all of them, was an admissible supersolution for each of the cubes. So in each one of the cubes, I have the solution of the problem with the polynomial data that touches over here, and I have the other solution which is above this one. So the contact set is smaller. Okay, which means that this quantity is subadditive. Okay, so sigma is subadditive is between 0 and the measure of q, and so sigma over q has a limit. Okay. Now sigma over q has a limit, right? So now let's say what can we say about how far is the solution of the obstacle problem from the solution, from the real solution? Okay, so how far I may use an extra 5 minutes from the real solution. Okay, so this is measured by the Alexandrov-Backel-Mampucci theorem, which says the following. So you have, so let me make two observations. One is, okay, f of the square of u and x is 0 when it doesn't touch the obstacle. And when it touches the obstacle, is the same as f of the square of p of x, which is something bounded, because the quadratic polynomial, the square is bounded. Okay? And there is no distribution in between. The fact that the solution of the obstacle problem is the least super solution means that there is not a distribution in the part where u touches the obstacle. Because if not, will be an angle like that, and then the f of the square will be positive. Okay? If when u touches the obstacle is very nice, it's a polynomial. If u sort of touches at an angle, right, the d square of u can be positive, right, but it's negative. So it is bounded by above by 0. So it is between, so f of the square of u, this is something you can prove about the solution of the obstacle problem, is or this or this. And this is bounded by sigma, by the measure of the contact set, because this is bounded. So it is like a multiple of sigma. Okay? And so let me put together with this, let me put, I think we can erase this by now. Let me quote the Alexandrov-Backel-Mampucci theorem that says that if you have a solution of Aij dij of v equal to f, which vanishes on the boundary of a domain, then v is smaller or equal than the ln norm of f. Okay? So I take the big picture. I have the free solution, and I want to estimate how close they are. So I shrink to the size of order epsilon, right? So if I shrink to the order epsilon, I have this, I have the, everything is invariant by quadratic rescalings. I have this, I have the free solution. Now we are in the cube of size 1, right? And f of d square of u x minus f of d square of the free solution u0 x, right, is an equation with bounded measurable coefficients. The difference of two solutions is a solution. This is, Fij is the d square, f of a matrix minus f of another matrix, right, is the derivative of f at a point in between times the difference of the matrix. Okay, so it's Fij times, okay, the difference of the matrix, so it's d square of u bar minus u0 equal to the normalization of sigma, sigma over q, which is what is converging to lambda. So if lambda is 0, this says, okay, if lambda is 0, it looks like first like the solution of the obstacle problem may be separating from the polynomial, right? But doesn't matter. What is important is that if lambda is 0, the solution of the equation starts to align with the polynomial because it gets closer and closer. I mean, starts to start with the solution of the obstacle problem, so goes equal or above the polynomial, right? Because the solution of the obstacle problem is above the polynomial, and the two solutions are equiconvergent because the right-hand side is going to 0. Okay, so if lambda is 0, I can classify this polynomial as a super solution of the limiting equation. Okay, because the solution sort of goes at least to the polynomial or above. So for my viscosity method, that's all I need. Okay. And now the problem happens if lambda, if for a given this lambda depends on the polynomial, right? Because I'm fixing the polynomial, and I'm doing all of this construction, and I get the ergodic limit for that polynomial. So for each polynomial, I get a different lambda. If lambda is 0, my polynomial is a super solution. I am done. If lambda is different from 0, then let me make a little picture for you. So suppose that lambda, so we are converging to a lambda 0 bigger than 0. Okay, let's say 1/2. Okay. And now let me take a large cube and divide it in many parts. Five shouldn't be 5, should be a multiple of 8, right? It's okay. Let's say this is 8 by 8 in a poetic. So I divide it in many pieces, right? In a fixed number of pieces, 64 pieces. And I take lambda larger and larger. Okay, and I have the contact sets here. For each cube, I have the cube contact set, right, of solving the obstacle problem in each one of the cubes. Okay. And as the cubes become larger and larger, this is converging to 1/2 of the cube. Okay? So in most of the array, let's say at least for 60 of the 64 cubes, I'm going to have something very close to 1/2. Okay? On the other hand, I have the contact set of the large cube. Okay? The contact set of the large cube is contained in all of these little pieces. But it's also converging to 1/2. 1/2 of the measure of the large cube. Which means that basically it has to cover a big portion of these ones. It certainly has to touch most of them. Because if it doesn't touch one of them, it loses 1/64. Okay? So as the cube gets larger and larger, this implies that the contact set spreads uniformly all over the cube. Okay? In other words, if the cube is very large, in each cube of size 1/64 is touching. Okay? So now if I go to the epsilon configuration, I shrink this, I have the polynomial, and I have that the solution of the obstacle problem touches the polynomial in each one of these tiny subcubes, 1/64, 1/360, whatever. Okay? So that means, and remember I said, and I never prove it, that the obstacle separates nicely, in fact, Helder continues to do, but separates quadratically from the solution. So since the solution of the obstacle problem touches so much in so many places the polynomial, it sort of sticks to the polynomial. It's getting closer and closer to the polynomial. Which means that the free solution is below the polynomial. It's aligning below the polynomial because the free solution is below the solution of the obstacle problem. Okay? So that means that if lambda is 0, this polynomial classifies as a super solution. Okay? Because when you, so that means that indeed there is homogenization, that you give me any polynomial, the free solutions end up being above or below the polynomial, okay, in one case or another, and this tells me what the operator should be. And you can check that if the operator is uniformly elliptic, the homogeneous limit is uniformly elliptic, that if the operator is convex, the uniform limit is convex, and so on. So you get the, and then you have to prove, it's a little bit technical, you have to prove that indeed any sequence of solutions converge almost surely to the solution of the limiting problem. So okay, I already overdid it, so let me stop and thank you very much.